So we have talked about phase diagrams, but the phase diagrams take in consideration if we get a change pressure. And so what we consider normal is 1 atm. And so 1 atmosphere, 1 atm is considered normal pressure. And that's the equivalent to 760 millimeters mercury, 14.7 psi, which is pounds per square inch, 101.3 kilopascal, all those kind of things. So when we talk about pressure, one of the things you have to look at is pressure changing, or are we staying at normal atmospheric pressure, which is just 1 atm. So we're going to now shift at how states of matter change if we stay at normal pressure, so normal 1 atm. So what I have here is I have a cup of ice, and we're going to heat it up. So I'm going to go ahead and heat it up. And you notice that the temperature is changing, particles are starting to move a little bit faster. And once it gets to 0, the temperature doesn't move, but we see changes taking place in the state of matter. We've got some liquid, we got some solid, but the temperature's staying the same. Now, once all these particles have broken free and become liquid, the temperature's rising again. So we can see a couple of the particles take off and leave by evaporation. They're leaving from the surface. And evaporation, remember, is a way that something can vaporize from the surface of the liquid, but without reaching the boiling point. So notice that this evaporation is taking place here before our temperature has gone up. So I'm going to go ahead and I think I must hit pause. There we go. Sorry. All right, so we're going to watch it melt again. Once it gets to 0, we're going to notice that the temperature stays the same. And then it stays the same until all the substance becomes a liquid. Now, once it all becomes a liquid, we're going to start seeing the temperature rise again. And the temperature is going to continue to rise until we reach the boiling point. And the boiling point is the temperature at which the pressure of the system equals out to the air pressure pushing down on it. And for water, that's 100 degrees Celsius or 212 Fahrenheit. So we're going to go ahead and let the water get up to 100 degrees Celsius, and then we're going to see what happens when we get to 100. So it's still going. Particles are moving a little bit faster. We can see them moving faster down here. We get to 100 and notice that our temperature is staying the same, but the volume of our liquid is going down. And that's because we're boiling, and so the particles are actually they're able to vaporize now. They're going from a liquid to a gas, and they're vaporizing. So as they go from a liquid to a gas, they're leaving the cup. And so we see the volume of the liquid go down, but notice our temperature still isn't changing, and we're still heating this. Now, once all the water vapor has been heated and left, air will fill back in this cup, and now notice that we can get the temperature to go higher because we're still heating this. So the air in here can now get heated to a higher temp. So this is called a heating curve, if I could talk, sorry. So what we don't always think about is that at the melting point and at the vaporization point or boiling point, that our temperature has to stay the exact same until everything has done what that says it will do. So what I mean is melting means it will go from a solid to a liquid. You can't go to a liquid until everything is melted. So our temperature flatlines. Same thing when we boil, okay? The temperature will flatline. So this is an example of a heating curve. So right down here, this is going to be your solid right here. This is going to be your liquid. This is going to be your gas. Now on this heating curve, this is when it goes from solid to liquid, so it will melt. In this case, this substance melts at 5 degrees Celsius. Now you have a liquid, temperature keeps rising. At this case, this is vaporization or boiling. And for this, the substance boils at 55 degrees Celsius. So when we're looking at heating and cooling curves, you want to first ask yourself, am I looking at a heating curve or a cooling curve? And in this case, we know it's heating because we can see that the temperature continues to rise on this curve. All right, we are now going to look at a cooling curve. Okay, right here. So in this cooling curve, we can see that the temperature keeps coming down. So this is going to be our gas. This is going to be our liquid. And this little one right here is going to be our solid. So right here at this temperature, which is a little bit under 100, is our condensation point. And then down here at like negative probably 110 is our freezing point. So cooling curves go the opposite direction. So same thing on this one. This one condenses at 100. It freezes at 0. Sounds like water to me. This one condenses at negative 30 probably, but it also freezes at about negative 60. So this one's kind of a crazy substance, all right? It has to get really down negative. So now you're going to try your hand and see how you do with these heating and cooling curves.